All right, and we're live.
Hello, everyone. Hello, everyone. Good morning, good afternoon, good evening, wherever you are. And welcome to the mission of the Women in Solar series, product by for Astronomy Outreach. Celebration of this year's solar month. This year's series this monthly series is highlighting the critical contributions of women working in solar physics, and we are join us. So you are very welcome. Today we have a special guest. We are honored to welcome Dr. Marianna Korsos from the University of Sheffield. She'll be presenting a talk titled Catching the Spark, Predicting Solar Flares Before They Ignite. In her presentation, Dr. Korsos will ask you text both short and I'm sure you're all excited to hear her. Before we begin, maybe a quick reminder to everyone that this webinar is being streamed live on the OAO YouTube channel. So please put down your questions in the chat and we will relay them to the presenter. Thank you for being with us once again, and I'll hand over to Marianna. Thank you, Marianna, for being with us.
Okay, so I also would like to say good morning, good afternoon, or good evening to everyone, depending on where you are. And also I would like to thanks for the organizer for this invitation. I'm glad to be here. And I also thanks for the audience to come and listen to this talk. So basically this presentation is now dedicated to the tomorrow celebration of the International Day of Lights. And within this presentation, we would like to overview how we could catch the biggest firework on the sun before they ignite. Basically, morely, I would like to touch why it's important to predict them in advance and how we could do that or how we try to do that. So these big solar eruptions, actually called as the solar flares, on the video on the left-hand side, you can see a big flashes. And from this video, you immediately can see that the solar flares are a huge explosion on the sun and mostly happening in the lower solar atmosphere where the magnetic field lines are strongly concentrated. And this region actually called as an active regions. And within these active regions, the magnetic field strength is a couple of thousand larger compared to the quiet area on the sun. And these solar flares actually are sudden intense burns of the radiation, which is caused by the rapid release of the magnetic energy. And this magnetic energy actually is stored within this active region. And we can observe the flares from the radio wave to the gamma rays, almost full electromagnetic spectrum. And this is good because, for example, if you are focusing on the right-hand side image and the right-hand side corner of the image, you can see different images which taken with a different wavelengths from the same flare event. And if you compare these images, basically all of the images is revealing some structure of the flare, but actually some of them I cannot see on the other picture. And this is good because in that case we get more details about the flare processes, so we could get more information, and even this information can use to build up a more accurate prediction methods that we can use to predict them in earlier. And usually flares can last for minutes to hours, depending on the magnetic environment of the flares and also the strengthness of the flares. And the most energetic flares are usually accompanying with the so-called coronal mass ejections. And these coronal mass ejections can see on the right-hand side corner movies, So they are a massive cloud of the solar plasma and the magnetic field, which is erupting from the upper layer of the solar atmosphere. And this upper layer of the solar atmosphere is called as a corona. So basically, this is why we call this phenomena as the coronal mass ejections. And even sometimes we call them shortly as the CMEs. And the problem is, if this huge amount of plasma, what you can see ejecting all the time, rush straight to the Earth, because this interruption between the CME and the Earth's magnetic field can cause serious disruption in the space-based and the ground-based facilities. And actually, when we are talking about, we would like to predict the major solar eruptions, we're mostly focusing on the large energetic flares, the M and the X-class flares, what you can see on the left-hand side, and also those CMEs, what we called fast CMEs. So basically, the CMEs have just almost two distinguished classification. I would say we call them as a slow CME and fast CME. The fast CMEs are which can propagate almost with 800 km per second, and this could affect our Earth environment. And the M and the X-class flare, we already know that from the history, they also can cause some disruption in our communication, especially the radio communication. So the M-class flare is standing for the medium class flares, and the X for the extreme class flares. And together, very often, we are referring to them as a major flare class. However, the C, B, and A class flares, they are kind of harmless. They are just a little firework on the sun. And we classify the flares based on the X-ray measurements, which is done by the GOES satellite. So basically, this is why we call them as the GOES flare classes. So as I mentioned, we mostly try to predict the major solar eruptions. And we are discussing the flares and the CMEs together, because if you see on the right-hand side images, on the x-axis of the image, we can see the classes of the flares. And you can see that the number of the CME actually increasing with the flare size. And top of it, that's why we are discussing this flare and CME more often together when we are trying to predict as a major eruption, but however, they are totally two distinguished phenomena. The flares are more about the lights and the radiation, while the CMEs are more involve a physical ejection of the solar plasma into the interplanetary space. And before we just jumping to the topic why we would like to predict them, I would like to show some overview video. So these major solar eruptions are mostly coming from the so-called active regions, where the magnetic field are strongly concentrated, and the magnetic fields are a couple of thousand stronger compared to the quiet period of the sun, a quiet area of the sun. So these active regions are emerging from the solar interior to the solar atmosphere. And in some cases, the magnetic field has a quick rearrangement. And this is what we call magnetic reconnection processes. And the magnetic reconnection is a so-called responsible for the flares and the CMEs sometimes. And the problem is when the flare, like here in the upper part of the image, and the CME, which you can see it's broken from the active regions, they start to propagate through the Earth. And this is the point when the new research area is coming, which is very wide. It's space weather. So we are more interested about the flares and the CMEs in a space weather perspective, because they can affect more seriously our modern technology. So the space weather practically is describing the condition between the Sun and the Earth, and now it's also including the Mars environment or the entire solar atmosphere. And the problem is when the CMEs arrive and interacting with the Earth's magnetic field, and basically this interaction or this meeting setting up a so-called geomagnetic storm. And depending on the level of the geomagnetic storm, we can see aurora borealis, for example, close to the equator, like for example, last year in May. I am sure everyone is almost remembering because aurora was seen almost all around the world, close to the equators. Or if the geomagnetic storm is much stronger, then we could experience radio blackouts in the communication, or the electric power grid system has some fluctuation, and because of this, the electricity supply can be affected, or sometimes the main transformer station can burn down and causing total blackout in one or two more countries, depending on the region, what the electric grid system is supplying. So let's see a little bit in the spatial and the temporal span of these storms. So for example, you can see the timeline with this arrow. So when the flares and the CMEs are erupting, especially the major flares, the X-class flares and the fast CMEs, then the problem is the radiation and the high energetic particle from the flare event can reach the Earth 8 minutes up to within an hour. So basically, we have a very tiny warning window. And this is the reason why we're trying to predict the flares as soon as possible. Because when the high energetic photons arriving close to the Earth, then the radiation level is increasing dramatically. And think about if the astronauts are outside from the shielded area of the spacecraft, then they get a higher doses than, for example, than their body can take. So it's a very huge health risk. Or there are some research which is saying that the people who are on the flight which is taking the route close to the pole, they also get a higher radiation. So most of the time when there are some geomagnetic storm or the radiation is increasing, the flight companies actually recommending the flights to take a longer route and avoid the pole. And also the the X-ray and the extreme ultraviolet light from the solar flares can ionize the Earth's atmosphere on the day side of the Earth. And because of this, the state of the ionosphere is changing. So the high frequency radio communication is affected, also causing some blackouts. And the problem is the high frequency communication is used by the military emergency services. And also the global navigation satellite, the GPS coordinate can be affected. So the calculation of the GPS coordinate can be, has a bigger error than usually we have. And the problem is when the CME arrive, the CME can arrive within 2 to 4 days. So it's much slower compared to the flares, but it has a bigger effect when it's hitting the Earth's magnetosphere. And this interruption of the magnetic fields can actually induce geomagnetically induced current in the power system or the pipelines and the railway network or the trans-ocean communication cable. And the extra current can damage these facilities. But the question is where these solar eruptions are actually coming. So most of the major solar eruptions are coming from the so-called solar active regions. But before that, I am sure most of you are already know the Sun has a so-called 11-year magnetic solar cycle. What does it mean that? So during the 11 year, the Sun activity is changing. So, for example, you can see here this hilly plots. So it means that one hill practically covering 11 years. So there are few years when we don't see any active region on the Sun, or time to time one is appearing but quickly disappearing. And after that, somehow the Sun is waking up, kicking the magnetic activity. So the number of the active regions, what you can see on this magnetogram observation, these white and black patches, these are the so-called active regions. So the number of the active regions starts to increase dramatically during the first 3 years of the 11 year. And after that, our Sun is very, very active, full with energy, so producing so many active regions. And this activity period, or this maximum period, could last 3-4 years, depending on the size of the or the activity. So for example, here in the middle of this middle here shows that during that 11 year, the Sun was more active compared to, for example, at the beginning. And when our Sun is getting tired, less and less magnetic active region appearing. And it's going back to the minimum value, so our Sun is kind of boring when we are looking at. And actually, during this one solar cycle, we could count 1,000 active regions. And out of these 1,000 active regions, about 250 active regions becoming a little bit magnetically complex, which makes them a candidate to produce solar eruptions. Like, for example, if you see the middle of the middle part of the Sun in the magnetogram observation, you can see that here the positive, the white, and the black, which is the negative polarity, they are more mixed, and also in the upper part. However, on the left-hand side, you can see that the positive and the negative polarity are nicely separated. And this type of active region doesn't really producing major solar eruption, but these one definitely producing. And out of these 250 active regions, actually, only just 10% of them are producing major solar eruptions. So that's why we're trying to predict them kind of on the medium time scale and the short time scale. So during the medium time scale, we already know that during the 11-year solar cycle, there are so-called solar storm season, which could last for a week or few weeks. It means that during that period, multiple major flare and CME eruptions are occurring, and from different active regions. And also there is a short time scale. With the short time scale, we are more focusing on the evolution of the individual magnetically complex active regions. And now I would like to spend a little bit more time on that. So on the video, you can see that how the active region is forming, how the new magnetic flux is emerging, and it's becoming more complex and complex. And to study their evolution and also predicting the upcoming large solar eruptions, we are using so-called predictor parameters. And these parameters are actually taking into account those physical measurements of the active region which are responsible for the flare occurrences. And what these properties could be, which showing that the active region actually ready to producing or launching large major solar eruptions. So the first one is the so-called data spot. So in the left-hand side, we can see that the white light observation of the Sun, and within this region, what we call data spot, because the positive and the negative polarities are very close together. And so when we see a data spot, we already can say that this active region has a high chance to produce some large eruptions. And also these two opposite magnetic field lines, fields, can separate it by the so-called polarity inversion line. And shortly, we sometimes we call as a pill line. So basically, during this polarity inversion line, the magnetic gradient is very, very high. So in that case, if the magnetic gradient is high, then there is again a chance to produce a large solar eruptions. And above a little bit in the lower solar atmosphere, above this polarity inversion line, a so-called filament channel is forming. So this filament channel is somewhere a couple of 1,000 kilometers above this polarity inversion line in the solar atmosphere. So this, we can imagine that as a plasma cloud. So the plasma is piling up in that region through the magnetic field. And basically this plasma suspended by the magnetic field arcade. And these filament structure actually could be the indicator, this active region not just producing flares, but also CME eruptions. And we can see a so-called, on the right-hand side, we can see the very oversimplified model, which trying to describe how the flares and the CMEs are actually involving in this type of active regions. So if you can see that this positive and negative sign, these are referring to the positive and the negative polarity of the negative polarity foot points of this magnetic field arcade. And this is separated by the so-called polarity inversion line. And above this polarity inversion line, this filament structure is forming, which is a kind of plasma cloud, which is suspended by this magnetic field arcade within the active regions. And the reconnection site, what I showed in the video already, actually happening below this filament structures. And this reconnection site is actually happening when the positive and the negative polarity is field lines are forcibly pushed together, like in these little cartoons, and the so-called current sheet is formed. And within this current sheet, the positive and the negative polarity can reconnect and forming a new magnetic field lines. And these new magnetic field lines actually wants to leave this area very quickly. And also due to this process, the high energetic particles which are in this region, they are accelerated. So basically this magnetic reconnection process is converting the magnetic energy into heat and kinetic energy. So what does it mean? So basically during this reconnection, two particle streamline happening, one downstream and one upstream. The one stream is actually colliding with the surrounding plasma somewhere in the lower solar atmosphere, and this collision is heating up this plasma. And the plasma wants to cool down by radiation. So basically, this is the flare processes. And after that, this reconnection site actually is propagating upward, which makes this upper part a little bit more stressed. And as it's going up, this upper part reaching the so-called non-equilibrium state, so they are breaking up from the rest of the magnetic fields, which is anchored in the solar interior. And if they are broke up, is nothing to holding back to the sun. So they can leave it, they can erupt into the interplanetary system and also taking away the filaments. And this is the CME eruptions. And these magnetic reconnection sites, so basically the two opposite magnetic field lines can forcibly push together by the photospheric motions, like the twisting motion of the two opposite magnetic field lines or the strong shear along the polarity inversion line. And time to time also the new magnetic field lines is emerging and pushed over the pre-existing facts. And based on this configuration, so many flare and CME model exist in the literature, but still this oversimplified model can kind of describe nicely what we observably seen. And however, these polarity inversion line, filaments, and delta spots are not really enough to really predict the upcoming event well advanced. We just say that, yeah, we can see that structure, so maybe it will produce or not. So that's why we are deriving more parameters from different type of observations. So for example, we can take observation with continuum observation, but from them we cannot really derive so many parameters. Or we usually study the solar atmosphere with UV wavelengths or radio or gamma observations. But still, the problem is we still doesn't really get that amount of information what from the magnetogram observation. So in the UV images, basically what we can see, the active region starts to activate. So it means that more and more brighter area is appearing. And based on this intensity changing or the number of the brightening area, showing that probably there will be a large solar eruption soon. But basically we just see that the active region get excited. However, based on the magnetic field observation, as you can see from the partial list, we can get so many information. And the most accurate prediction methods are basically based on these parameters. And now I would like to show just an example, as these parameters also not so accurate at the moment, and we still have need to further improve them. So we already discussed the most major flares are coming from the magnetically complex active regions. So in that case, I would like to show two magnetically complex active regions. The upper one produce one X-class flare, but the lower active region actually didn't produce any large solar eruption, only just C-class flares, which is harmless. So anyway, in the first row, you can see one parameters. I don't want to go into details. So anyway, this parameter was identified as a good predictors, and this parameter was developed based on a statistical analysis. So when this parameter was created, after that, this parameter was calculated on the flaring and the non-flaring active region cases. And after that, based on the statistical analysis, the person who identified this parameter, they said, if this parameter crossing the threshold level, which is highlighted by the blue horizontal line, then there is a 70% chance this active region will produce a large solar eruption in the next couple of days. However, look at both of the active regions cases. This parameter actually crossed the threshold level, and only just the upper active region produced flares. Let's see the second column. Here again another parameter. Also it has a threshold level based on statistical analysis. So in the peaceful active region cases, which didn't produce large solar eruption, actually this parameter didn't cross the threshold level. This is good. But in the active region which produced the flare, large flare, you can see that the parameter crossed the threshold level time to time, and it was continuously above few hours before the flares. But however, after the flares, this parameter actually increased further. But this parameter, this active region didn't produce other flares, or maybe when it's turned the far side of the sun, then probably maybe produce one flares, but we don't have any information about that. So basically this study actually it's want to highlight that one parameter is not enough to predict a flare. We need more parameter to develop better flare prediction methods. And also maybe if we are combining them or found common properties of these parameters, then hopefully it give a much better accuracy. So where we are with the flare prediction today? Currently, our flare prediction efforts are mostly probabilistic. So basically, we are just giving an estimation. There will be a major flare or not in the upcoming day. And this upcoming 24 hours is always pushing further until the active region not died or become less magnetically complex. And the forecast window, some of the parameters just giving prediction for the upcoming hours and others giving information for the upcoming days. However, in both of the cases, the uncertainty is increasing because the problem is on the short forecast window scale. This reconnection process, which is triggering the solar flares, it's happening very quickly. And we still don't have these routine observation to unobserve this tiny scale when they are erupting. And at the longer forecast window, the uncertainty arises because the active region itself is changing very quickly. So typically, the magnetic field structure can change within 10 to 24 hours. And also the problem is we cannot predict the exact class of the flares because an M-class flare is causing less problem than the X-class flares because the X-class flares is 10 times larger than the M-class flares, for example. And the other problem is we don't know the active region will produce CME or not with the large flare eruptions. And of course, now in the literature, we have more than 100 predictor parameters. So that's why researchers started to test these parameters and compare their prediction capability. And they found that only just 30 parameter is promising as a good predictors. However, none of the parameter outperforms the others from out of these 30 promising predictors. And actually all the parameters failed on that subject. They cannot predict the first flare and the last flare of an active region. And what is still missing? An active region can live for a week or can cross the sun within a week. So in that case, it would be so good if we would know when the active region producing a series of flares and when it has a quiet period, because during 1 week, if the astronauts can go out for even just 1 or 2 hours, then it would be a big help. Then they are just sitting for 1 week until the active region will move away. And maybe another one is coming, so again, they have to stay for 1 week. So what could be the missing bits? At the moment, we have magnetic field information only from the solar surface. And you had seen in the previous slides, the best predictors and most of the predictors can be derived from the magnetic field observations. And this is the problem. We don't have routine magnetic field measurement from the lower solar atmosphere. And why we need this? Because the solar eruptions are not occurring on the solar surface, they are occurring somewhere in the lower solar atmosphere. And some of the researchers are already realizing that. And also now there are projects which are moving forward to proposing those satellites which are ground-based satellites, ground-based observations, which are measuring the magnetic field through the lower solar atmosphere. And this would be a big help to improve our prediction methods. But until that, we need to use other methods. And in the literature, we have a so-called mathematical modeling, which help to model the 3D magnetic field structure of the active regions. And for that, we can use as lower boundary condition, the photospheric magnetic fields. But however, the question is, which model is the best? So we already did some comparison analysis based on that, which model would be a more accurate or the more relevant to use in a space weather prediction purposes. So basically now researchers identifying that the parameters should be not just calculated based on the photospheric magnetic field, but also from magnetic field at higher up in the lower solar atmosphere. So in that case, you can see on the right-hand side upside a magnetic field observation and the UV image, and these two observations is combined. So basically, with the UV images, we can see the magnetic loop structure, while with the magnetogram, photospheric magnetograms, you can see the polarity. So the blue is representative of the negative, and the red one is for the positive foot points. And globally, if you can see four extrapolation techniques, what we call as magnetic field modeling. And you can see that globally we can nicely get back the magnetic field loop structure of the active region. But however, in details, it's sometimes between these four extrapolation techniques, we can see that the magnetic field lines are connecting maybe a little bit to the other polarities, not the same one, or even the tilt or the direction can be different. And based on this study, we found that actually in globally the evolution of the parameter is similar. However, the fluctuation of the parameter through the time can be changed, and also the value could be different. So basically, we conclude that it doesn't matter which one you are using, but you should be aware which one is the most fastest one, because for the prediction method we need fastest one, but also we need to be aware with the limitation of the extrapolation techniques. And why we are using that, I just would like to highlight that how could it improve the prediction capabilities if we are extending the application of different parameters in the lower solar atmosphere. So when we constructing the magnetic field structure of the active regions, we could make a horizontal cuts. And it means that we could get a 2D magnetic field map at a certain atmospheric height. And in our case, we are comparing the evolution of the different parameters at different atmospheric height. And we found that some of the parameters are actually changing the how they are so how their evolution is through the atmosphere in time. So for example, here the purple one is referring to the photosphere, while the yellow one is referring to the 10 megameter above photosphere. But however, in that case, the evolution looks like the same, only just the value is changing because, for example, this parameter is including the magnetic field value. And we know that the magnetic field, as we're going up, it's decreasing. So this is what we kind of expecting. But there are parameters which actually can calculate it for some of the height, and above it, it's impossible to calculate. And what we found, let's focus on the right-hand side, these columns. So the most important things is on the x-axis, we can see the investigated heights. And the X-class flares, the analysis is referring to the last 5 active regions, and the number of the active region what was studied and produced X-class flare is highlighted with this bold-faced number, and the upper 2 is produced just an M-class flare. So basically, from this figure, we can conclude that there are more empty space here which is relating to one parameter than in the X-class flare cases. And basically from this plot, we could get that information, or that if more parameter is satisfying the pre-eruptive condition at higher up, that's relating that this active region will produce a larger, most energetic flares. While less parameter is satisfying the pre-eruptive condition higher up, then this active region will produce a less intense flares. And also, we separated those large energetic flares which occurred with CME or occurred without CME. And we found that if the parameters, most of the parameters are remaining below 1 megameter, then these active region producing just flares. However, if the parameter is still satisfying the pre-eruptive condition above 1 megameters, then these flares actually accompanying with the fast CMEs. So basically, we found that if we are extending the application of the different parameters in the lower solar atmosphere, we could improve the prediction based on what type of intensity what we could expect, and maybe also we could give information about the active region producing only flares, or we are producing flares and CMEs. And just if I would like to take a few minutes about the medium time scale, especially because this is just getting a new direction in the space weather research or the flare prediction research. I already told that the sun has a so-called solar storm season, and from long time ago, we know that the active regions at the beginning of the cycle, they are appearing at the higher latitude, and at the end of the cycle, basically, they are getting close to the equator. And in the new cycle starts, then the sunspots or the active regions also starts to appearing on a higher latitude. However, there is other phenomena which is still under a debate. This is called an active longitudo. And actually, I listed most of the papers which studying this active longitudo, and you can see that the list is not really long. And there was a period when it was discussed, and after that, for a long time, it was kind of neglected, and now it's getting back again. However, there are researchers who says that this active longitudo only just can be coincide with the random fluctuation rather than the real phenomena. But those people who are supporting that idea, but unfortunately, theoretically, still cannot really explain why is it. But observationally, it was found that within this active longitudo, when it's can be observed, then the flux emerging is very strong. It means that due to this quick and very strong flux emergence, the magnetic complexity active region appearing more often than in other longitudes. And if there are more magnetically complex active region in these the longitudinal belt, then it also means that all the flares could be occurring, the major flares could occur from that regions. The problem is these active longitudes just persist for 2 or 10 Carrington rotation, which is mean that a few months up to half a year. And of course, during this half a year, not all the time is active. But anyway, if there would be an opportunity to somehow predict the evolution of these active longitudes, then definitely it would be help us to reduce the computational time to focus on these magnetically complex active regions which are sitting on this active longitude. And when in that case, after that, we could go for the individual study of these magnetically complex active regions and measure the magnetic field through the lower solar atmosphere, or do the modeling of their magnetic field structure, and even compute the different prediction parameters and conclude that what will be the size of the flare or the active region producing a flare with the CMEs. And thank you very much.
Thank you so much, Marianna. Thank you for the amazing talk. I'm sure our participants have enjoyed all that you've shared about solar flares and predicting when they happen. And we are happy you are doing this work to protect us and to know about what's happening on the sun. So thank you very much. We will now move on to the questions that we have from our audience. We have one question from Cornelis Annie, and the question is, do CMEs occur near or depend on sunspots?
The CMEs occur near or they depend on. So the CMEs have different procedures. So for example, not all the CMEs are occurring from the sunspots. The simple reason is sometimes there is a long filament which is almost crossing half of the sun. They are could occur and they are not close to the sunspot, but in statistically, most of the dangerous CME are coming from the sunspots. I hope it was an answer for that question.
Thank you very much. We'll move on to the next question from Bostina Khalil, and it says, please tell us how to predict values of solar flare in the following solar cycles.
Values. I don't really understand the question, but if you are mean that yeah, which yeah, thank you. So which models? To be honest, the most those parameters or predictor parameters which are relating, including the polarity inversion lines, the helicity, magnetic helicity, which give information almost about how the magnetic field structure of the active region is complex. Also, it's a very good indicator when we are calculating how many free energy in the system, because this free energy is converted to the flare. So if we have more free energy, then probably it will produce larger flares. Also, how big is the magnetic gradient or the shear along the polarity inversion line? I would say these type of parameters, and we could combine them so we could make it weighted length of the polarity inversion line, or how big is the internal connections within the active regions, but definitely which including the polarity inversion line, the magnetic field information, and how the complexity of the magnetic field. These parameters or these prediction models are more accurate, I would say. And we can add a little bit extra information, but mostly these categories are the more better one.
Amazing. Thank you for the answer. I hope, Bastina, the question has been answered. The next question is from Brigitte, and it says, do you think that AI can help with these predictions, or are you even currently using any AI to help with your predictions?
Thanks for Bridget for coming. Yeah, this question. I think there is two groups. Someone saying yes, definitely it's helping us. Before the AI come, at the beginning of the AI, I was really amazed with that. But now, as I also using it, I went back to the more studying the parameter individually, how they are developing, and I using the AI just for as a statistical analysis. I would say the problem is with in our case, because we have less positive cases than negative cases. So in that case, the AI, I think, influenced by the so many negative cases, and we just cannot produce more positive cases. So because of that, I would say the AI is very nice to test our models and do a quicker prediction method, but definitely with, I would say, still the human predictions are much better than the AI ones. And actually I was kind of surprised how the real flare prediction is or forecasting is happening. Practically the forecasters are sometimes overwriting the model predictions, because the best predictors actually the forecaster who are doing this work in a long time, because they know exactly or based on experience. So I would say it's just helping us, but we are a little bit far away to use just and or rely on AI predictions.
And are there any ongoing tests to make it much easier, or to train the AI to help you have more accurate, predictions?
Yes, so now the physics informed AI is coming, and I think this is a huge step, because uh, at the beginning, and I see the question of the Khalid. I try to answer yours and Bastian question. So the problem is with the simple statistical and deep learning method, it doesn't include physics information. It's just a data, image, and the AI tried to find some common properties. However, with the physics-based, we can improve the prediction method of the AIs, because the physics is the most important essence of all the models, I would say. Application deep learning model to predict the soil. So today we can combine all kind of difference of AI method, and yeah, sure, we can use the LSTM with the deep learning, but again, no physics in it. The best if you are including also physics based. But if you go in the literature, you will see that how the simple machine learning is combined with the deep learning method and etc., and build up prediction methods.
Thank you, Marianna. So while we're waiting for more questions, I want to know, but maybe you can help us, tell us a short story about how you got into predicting solar flares. What was a journey to doing this incredible science of predicting solar flares to protect us from all the harm and interesting things that's going on?
So that's kind of interesting, and I think a funny story, but this is a real story. So I did my master in cosmology, and after that I moved to the industry for a couple of years. After that my contract ended. I went to I started to search for a job, and accidentally I found a job in Hungary in a solar observatory. They look for an observer, and I applied for that. And after a year, they asked, I would like to do some PhD or something like this. So basically, I did my PhD a little bit later on after my MSc. And basically, they had a project about the flare prediction. And I said, yes, I would like. Why not? And that was the point when I started to work in that direction. And I
Wow,
started.
you have a very interesting journey. So I know that astronomy has different areas, and you moved all the way from cosmology to solar science. Was the shift very difficult? Because I know it's kind of very different. Cosmology is all the way out there, and then the sun is so close to Earth. Was it difficult moving from cosmology to solar
Um,
science?
Of course, so I think the most difficult part was I had 6 years in the industry, so I didn't do any astronomy stuff. So basically, to pick up again the knowledge and what was done during this 6 years in the research, but because I am more focusing on the data analysis, I think to work with the data, it's almost the same, but the important is how we are interpreting the result. And probably that was the hardest part, but thanks to the supervisors, it went smoothly. So of course, the beginning is hard to pick up what was going on in the research, but if you spend enough time, you could pick up, and also speaking with colleagues, going to conferences, then it will help you to get into the topic.
Amazing. Thank you so much for sharing your story with us. I don't know whether we have any more questions from our audience. Um, if not, I want to say thank you very much to Dr. Marianna Korsos for joining us in our May monthly series on women in solar physics. Thank you for your time and for sharing with us your incredible research
Thank you.
that is here to protect us and to help us plan for solar flares. So thank you so much. And we are going to keep everything you said in mind. And we are really grateful for your time.
Okay, thank you very much. And if
Thank you so
anyone,
much, Dr. Mariana. And thank you to our audience for joining us.
okay, thank you.
Please go
Bye.
ahead.
No, I
No,
just
wait.
saying, if you have a question, please just feel free to email me, and I am happy to do discussions.
Thank you so much. And thank you to our audience for joining us. And I hope that you keep in touch with us on our social medias and look forward to updates from us. We will have another session of the Women in Solar Physics in June, also June 20th. So look forward to our notifications, and we hope to see you next month. Thank you for joining us, and have a wonderful morning, afternoon, and day.
Okay, bye. Thank you.
Bye, everyone.